An inverse function is a function that undoes the action of another function. So if we say g is the inverse of f, that's true whenever y equals f of x. If we have y equals f of x, then x has to equal g of y. So let's do a couple examples that will hopefully solidify what's going on. So if I have, for example, some point on the graph f of x, let's say it's 7 comma 21, then there must be a point on the graph of g of x, which in this case, g of x is the inverse of f, which is often notated f negative little negative 1 of x. So that means inverse function. So if I have g of x being the inverse function of f, that means that whatever the y value was on f, it has to map it back to whatever the x value was on f. So ultimately, taking f of 7, getting 21, then taking g of 21 gets me back where I started. That's essentially what an inverse function is. It gets us back where we started. If we did the original function, I can undo the original function's action with g. So if I make a function f of x equals 3x, and my inverse function is x over 3, I know that these are inverse functions because if I take any value, for example, 7, 3 times 7 is 21. If I take 21 and divide it by 3, I will then get 7 back. So these two functions happen to be inverse functions. And that would be true of any points that I chose to put on here. So let's say I had -3, -9. Notice that if I take 3 times -3, I get -9. If I took -9, -9 divided by 3 gets me -3 back. So any values work here. That's why these two are inverse functions. It's possible that I have one such point that works or something, but it's not true all the time. In order for something to be an inverse function, this has to work for all values on the domain. Okay, so this has to work for all values in the domain of both functions. Sorry, I ran out of room. Can I have inverse relations? So that's a little bit of a trickier concept. We'll get back to that in a second. We'll answer this question first in order to understand it. Are y equals x squared and y equals square root of x inverse functions? Well, let's take this to be f of x, and I'll call this f inverse of x. So f of x is x squared. Let's say I take the point, the value 2. So if I take f of 2, that's 2 squared, which is 4. Then on f inverse, if I substitute in 4, I have the square root of 4, which is 2. Notice that 2 comma 4, then f inverse took me from 4 back to 2. That's good. But that doesn't work all the time, because if I start with f of -2, I get -2 squared, which -2 squared is actually positive 4. So then I take g of 4, and I get the square root of 4, which is 2. So -2, 4 did not get mapped back to its original value. I started with -2, I ended with positive 2. So that's not good. That means this is not necessarily an inverse function over here. These are inverse functions. Once again, on the domain where it works. So if I restrict the domain, then I can get inverse functions. So y equals square root of x had a domain of negative or 0 to infinity, and the range was 0 to infinity also. Since that is the case, over here, the domain and range must be restricted so that the range of my inverse matches the domain of my original, and the range of my original and the domain of the inverse have to also match. They have to match because everything that's in the domain over here ends up getting moved to the range in the inverse function. Remember that if there was a 7 in the original function's domain, there had to be a 7 in the new function or the inverse function's range. So in order to have an inverse relation, that's kind of odd or tricky. I mean, you technically could kind of do that. I mean, an example would be if I had a parabola like this, then I could technically have an inverse relation where it's a sideways parabola because everything gets mapped over. But then you kind of get in a tricky spot where you don't know which value is going to come out. Because in a relation, you don't necessarily know if I have an input of 3 here, I don't know if this value or this value is going to come out. So there are some issues with them. Okay. Sorry. What are one-to-one functions? Why should I care? And how easily can I decide if I have a function that is one-to-one? So a function for which every element of the range corresponds to exactly one element of the domain is a one-to-one function, and those are also called injective in mathematical terms. So if you go to college and they use the word injective function, that's something that you might want to know. Um, we know that y equals f of x is only a function if we pass the vertical line test. An easy way to tell if something is injective or one-to-one is if it passes the vertical line test, because it has to be a function, and the horizontal line test. Horizontal line test means after it passes the vertical line test, the horizontal line test means that there is exactly one element of the range for every element of the domain. Here's an example of something that does not work. Once again, a parabola. If I take the vertical line test, it is a function. But if I take the horizontal line test, notice that two different elements of the range, or I'm sorry, two different elements of the domain have the same element of the range. So I have two domain elements that go to one range element. I know that there will not be an inverse anytime it doesn't pass the horizontal line test because, or there won't be an inverse function because if I then flip the domain and range, that means I have one domain element going to more than one range element, and that's bad. So therefore, the horizontal line test has to be passed in order for something to be one-to-one. And why should I care? Because if you're one-to-one, that means that you have an inverse. If you're not one-to-one, you can't have an inverse. Finally, say that G is the inverse of F. What does that mean about G of F and F of G? If I have G of F of X, let's, for example, recall that if I have any point on the graph of F let's call it AB. Then on the graph of G, these points are going to be flipped. So let's take G of F of A. What happens to F of A? It turns into B. G of B gives me A. Likewise, if I take F of G of B, I get F of A, which is B. Notice G of B gives me A, and then F of A gives me B. Notice in both cases, what I started with and what I ended with are the same. So if I take G of F of X or F of G of X, I should end up getting exactly what I started with. I should get X back. So I get what I started with. I'll write it down just to make sure we get it. I get what I started with. So in order to specifically answer the question, what does that mean about G of F of X and F of G of X? They are both equal to X. Now let's start doing some problems. Given the points as written below, what we want to do is we want to find 5 points on the inverse. So what we should remember is that all of these points are going to have their x and y values flip. So that means f inverse of x is going to have the following points: 4, -2, 7, 4, 0, 11, 0. -8, 3, and 10, 10. So again, everything flipped. Now notice that 10, 10 flipping still gives me 10, 10. Is this a one-to-one function? Basically, in order to tell if it is a one-to-one function, what I want to do is I want to look at all of the x values and make sure that they have exactly their own y value. So that's not something I wrote yet, but that might be something you want to go back to the one-to-one thing and make a note of, is that every x value has its own special y value. Okay, that means that it doesn't share any y values. So for example, in this one, notice that, let's say this is -3 and +3. They shared a y value. That was bad. So I need to make sure that I don't share any y values if I want to have an inverse function. If I look at these, 4, 7, 11, -8, and 10 are all not shared. They're all solo things. So that's good. So that means it might be one-to-one. The reason we don't know if it's one-to-one for sure is we're only given information about 5 points. So maybe there's some other point that's the point 8, 10 that we don't know about. And then 10 might be shared. So then if I had this point, 10, 8, and the inverse, notice that then I would have 2 different values when I plugged in 10, and then that couldn't be a function. Now, are we aware of a point 8, 10? No, but it's possible that it exists. And so this might be one-to-one, but it isn't a guarantee. All right, now we're going to find the inverse of this. Let's talk about how to do this algebraically. If I want to find f inverse, the first thing I do is I write y equals 15x minus 1 I'll just change it to a y. What you always do is flip the x and y and then solve for y. That's the process, because what we've noticed the entire time we've done this is we've flipped the x and y values in every single point in order to get the inverse. So algebraically, it only makes sense to solve for it. We're going to flip the x and y values. So I flip where the x and y values are, and then I solve for y. So I'm going to add 1 to both sides. So x plus 1 equals 15y, and now I will divide by 15. So y equals x plus 1 over 15. The final answer, I'm going to write f inverse of x equals x plus 1 over 15. Letter B, y equals 1/3 x plus 7. Notice that I'm putting a squiggly line here. That's kind of just helping me remember that these two things are not the same function. I'm finding the inverse function. So when I flip the x and y, it's not actually equal to what I started with. So x equals 1/3 y plus 7. I'm going to subtract 7 and then multiply by 3. So I have 3 times x minus 7 equals y, and I can distribute and I get 3x minus 21. So f inverse of x equals 3x minus 21. Problem C. What I'm going to do to try and shorten the video is make sure that we are aware that I need to have a domain restriction on this function, but I'll figure that out when it's over. Okay, so what I'm going to do is I'm going to figure out what the range is of this inverse function, and then I'll make that the domain of my original function. Because the parabola y equals x minus 2 squared actually looks something like this. It's not going to pass the horizontal line test. So because it's not going to pass the horizontal line test, we have to do something about it. So y equals x minus 2 squared. I'm going to flip the x and y. So x equals y minus 2 squared. Square both sides. So I get x squared. I'm sorry, square root both sides. Good grief. It must be 10:21 at night when I'm making this. Sorry. So square root of x equals y minus 2. So I square root both sides. Notice that normally in equations, when I square root both sides, I put a plus or minus, but that wouldn't be a function anymore, because if I had plus or minus, it would look something like that. So I'm not going to put the plus or minus. I'm just going to keep it positive for simplicity's sake. Then I'm going to add 2 to both sides. So square root of x plus 2 equals y. So f inverse of x equals square root of x plus 2. If I look at the domain of this, that is from 0 to infinity. It's from 0 to infinity. So when I'm doing the range, that means that I kind of look at this. If I sub in 0, I get 2, and so on. It keeps getting bigger and bigger. The range of my new function, my inverse function, is 2 to infinity. Remember, the range of this has to match the domain of my original function. So I'm going to restrict the domain of my original function to be 2 to infinity. So that's something that's kind of important, understanding that I have to restrict the domain of my original function, because this wouldn't match up with everything if I plugged in all real numbers. Finally, letter D. There are no restrictions on anything that's a cubed root or anything like that, because I can sub in any number for x. So let's flip the x and y. So x equals the cubed root of 5y minus 24. I'm going to cube both sides, subtract, or I'm sorry, that should be a minus 24. It's almost miracle working there. I'm going to add 24 and divide by 5. So x cubed plus 24 divided by 5 equals y, which I'm just going to write as f inverse of x. Finally, we're going to graph the algebraic inverse. Graphing, you can do this in two different ways. Notice that I have the point 0, 1 on the graph. Remember that x comma y's get flipped to y comma x's when I'm graphing the inverse. So if I have 0, 1, that's going to be 1, 0. If I have negative 2, 0, that's going to be 0, negative 2. If I have negative 4, negative 1, that's going to be negative 1, negative 4. And so this graph kind of looks something like this. Well, not like that. Wow, that was brutal. Um, this is not nearly as easy as it is on the actual smartboard. So let's try something like this. Much better. Kind of close. Not quite. Okay, finally got something. So that's my inverse function. Over here, notice that this doesn't pass the horizontal line test. That's a big problem. So since this doesn't pass the horizontal line test, then what I'm going to have to do is I'm going to have to restrict the domain. So I'm going to restrict everything. I'm going to kind of pretend like this doesn't exist, unless I wanted to do a an inverse relation, which would kind of be a sideways parabola. But I'm just going to pretend that that doesn't exist. And then what we will do is if I see the point 0, negative 3, that's going to turn into the point negative 3, 0. I see the point 2, 1, that's going to turn into the point 1, 2. It looks like 1, negative 3 is on there. So that's, I'm sorry, 1, negative 2. Thanks for reading. Sorry, my fault. So that's going to be negative 2, comma 1. And the graph will look something like this. So notice the red and green. Now, what I'm going to do is I'm going to draw the line y equals x, or at least something that's kind of close to the line y equals x on the graph. And so when you look at this, what you can see is that points get reflected over the line y equals x. Notice they're the same distance away. Well, they would be the same distance away if I drew this line a little better. So the line y equals x would actually go kind of through here. So notice that there is a reflection over y equals x for inverse functions. So inverse functions reflect over y equals x.